All right, so we're going to put all of these pieces together and start to try to figure out what graphs look like, including where the location of all of their maximums and minimums are, where their inflection points and then see what we can sketch without even looking at a calculator or at Desmos. We can always verify with our calculator or Desmos afterwards. So I'm going to start by finding and classifying the local extrema for each of my functions, and then listing intervals of increase and decrease. Notice that this is my first derivative test. And then we'll find inflection points and list intervals where it's concave up and concave down. That's going to all be based on my second derivative. And then finally we'll use all of our information to sketch a graph of our function, clearly showing everything that we found. So here's my first function, fourth degree polynomial, and I'll begin with my first derivative test. F prime would be 4x cubed minus 6x squared. Again, never undefined, so I'm only going to worry about where it's equal to 0 to find my critical values. I can factor out a 2x squared, gives me 2x minus 3. So it looks like x equals 0 and x equals 3/2 would be the critical values for that first derivative test. I know that my first derivative is 0 at both of these places. That's how I found those numbers in the first place. And then if I want to go ahead and test some values, let's see, let's just put that first derivative in the calculator. That way I can use the table. And I'll pick a test value in this furthest left interval. Anything less than 0 will do. Let's do -2. And it looks like my derivative is negative. Pick something between 0 and 3/2. So how about 1? And it looks like our derivative is still negative. Finally, pick something bigger than 3/2. I'm going to go with 4. Definitely positive. So this says that my function is decreasing again, and then increasing. So even though 0 was a critical value, there's no maximum or minimum at 0. The graph decreases on both sides of it. No max or min. M&M's, my abbreviation for max and min. Here, though, we were going down and then up, so this is a minimum. At x equals 3/2, and I'll get the y value for that in just a few minutes. All right. Let's see. I'm going to leave that y value for now until I put the whole function in my calculator, which I will do. But let's do our second derivative test next. F double prime would be 12x squared minus 12x. And again, never undefined, so I'm just asking myself, where is that equal to 0? I can factor out a 12x and get x minus 1. And it looks like x equals 0 and x equals 1 are critical values for that second derivative test. So I already know that at 0 and 1, my second derivative is 0. And then I'll pick some test values here. I'm going to put my second derivative in the calculator. And let's start. Got -2 in there already. We might as well use it. -2 looks like our second derivative is positive. Between 0 and 1, maybe I'll use 0.5. And it looks like our second derivative is negative. And then let's try 2, positive again. So second derivative tells me about concavity. This is concave up, concave down, concave up. That means that I do have a change in concavity at 0, meaning I do have an inflection point at x equals 0. I'll fill in the y value in a minute. And another change in concavity happens at 1, so another inflection point when x is 1. All right, so we've pretty much located all the important points on the graph. I'm going to go ahead and put my original function in my y equals now so I can get all the y values that I wanted. And let's see. We needed the y value for this minimum, which was 3/2 or 1.5. Looks like y is negative 1.69, let's call that. Zero should be 0, 0, 0. And then the last inflection point was at x equal 1, and y is negative 1. All right, I'm going to go ahead and graph this. I haven't listed those intervals yet. We'll do that, but let's go ahead and while all of this is fresh in our minds, let's see if we can graph our function. Don't need very large values or very small values for this one. I know that there's a minimum at 1.5, negative 1.7-ish, so somewhere around here. I have an inflection point at 0, 0. And another inflection point at 1, negative 1. So let's think our way through this. This graph is decreasing at first, which makes sense. It's going to come down towards that minimum. And it's decreasing but concave up. So when I start to draw, I'm going to draw a function that's going downhill but bending upward, concave up. One other thing before I start to draw. Notice that at 0, 0, even though there was no max min, my derivative is 0, so I should have a horizontal tangent line there. So I'm going to start drawing this coming decreasing but concave up. And as I come in towards that inflection point at 0, I'm going to make my graph level off and go temporarily horizontal right there. It's an inflection point, and it has a 0 derivative, or a horizontal tangent line. All right, leaving that inflection point, I'm going to change to concave down. So again, kind of come out of this sort of horizontal and concave down until I hit the next inflection point. And then I'm going to change to concave up again, go through this minimum, and then I'll keep on going up forever. Again, perhaps I'll hold off just a little bit and check the graph. Well, actually, you know what? This one, I don't think it's all that difficult to get the intercepts on this one. If I go back to the original and just set this equal to 0, because it factors so well, it looks like x equals 0 and x equals 2. So I need to come up a little bit more sharply here. I'm already going to go back through here at x equals 2. comes my little eraser? Is not. There we go. There we go. That's a little bit better. So there's my picture. Again, double checking, decreasing all the way to the minimum, and then increasing. Concave up to the first inflection point, concave down to the second, and then concave up for the rest of it. So that should be a pretty decent graph of what that function is going to look like. Now it is already in my calculator, so let's double check it. It's right there. And my window, it doesn't have to be very big this time. -4 to 4 is sufficient on both axes. And there we go. You can see that picture looking very, very much like what we just drew. So nicely done. Could have done it in Desmos as well, but got the calculator sitting right there. Lastly, I haven't done the intervals yet, so the intervals of increase and the interval of decrease, let's just list those out. Let's see. Increase is just from 3/2 to infinity. And decrease from -infinity to 0, and then also from 0 to 3/2. Notice that I can't just go from -infinity to 3/2, because right at 0, it's not decreasing, it's not increasing either. It's instantaneously horizontal there. So don't be tempted to join those together. You have to list them separately. Concave up and concave down. Concave up from -infinity to 0 and from 1 to infinity. And concave down just in the middle here between 0 and 1. All right, so there's our first graph. Well, let's try one that's not a polynomial. Both of the ones we've done so far have been polynomials, right? So maybe a little on the easier side. This one's going to have some exponentials in it. E to the x, subtract e to the minus x. And I'm going to go through the same procedure. Let's start with the first derivative test. F prime would be e to the x, subtract e to the minus x, and then chain rule times the -1 there. So that's actually e to the x plus e to the minus x. And I don't have to worry about that being undefined, so let's just ask again to get critical values. Where is that equal to 0? Your choice as to exactly how you want to look at this. I often will follow a little technique, and you're going to see me use this in the next couple of examples, whereby I'll factor out the smallest power of whatever I'm working with, in this case e. So if I factor out e to the minus x, it's going to make this first one e to the 2x, right? That way when you add them together you get e to the 1x again, plus 1. So e to the minus x equals 0, or e to the 2x plus 1 equals 0. Now if you think about your exponential decay function, it's got an asymptote, right? On the x-axis, it's never actually equal to 0. So I actually know there's no solutions to that, or if I wanted to be formal about it, I could take the natural log on both sides. But the natural log of 0 is undefined. Your calculator will tell you that as well. So no solutions to that one. And how about this one? E to the 2x equals -1. Kind of the same problem. An exponential function never goes below the x-axis, but once again I can be more formal about it. If I take the natural log on both sides, you can't take the natural log of a negative number, or at least it's not a real valued number, so I'm once again going to say no solution. So I actually didn't get any critical values for my first derivative test at all. What that means is this function is going to either be increasing all the time or decreasing all the time. So I can check on that just by picking any test value at all. So there are no critical values to put on my number line. I'm just going to say pick any test value. Let's do 0 to make life easy. And if I plug 0 into my derivative, e to the 0 plus e to the 0 is 1 plus 1 or 2. It's positive. So what this tells me is that my function is always increasing, and there are no maximums or minimums. All right, let's do the second derivative test. Let's see, this was the simplified form of my first derivative right here, so I'll take the derivative of that and get e to the x, and I'll have an e to the minus x, but the chain rule is going to give me a times a negative 1, so that'll actually be a minus there. And once again, I don't really have to worry about it being undefined, so I'll just ask myself, where is that equal to 0? I'm going to use the same trick. I'm going to factor out the smallest power of e, so e to the minus x. It makes that e to the 2x minus 1. Again, remember, you're really taking x minus a minus x. That's how I'm getting that 2x, but you can double check. When you add those together, you get the x back again. So e to the minus x equals 0, or e to the 2x minus 1 equals 0. We've seen this one before. When we try and take the natural log of 0, it's undefined, so there is no solution. But this one's a little more interesting this time. This would say e to the 2x equals 1. So if I take the natural log of both sides, ln and e are inverse functions, so I'm just going to get 2x equals the natural log of 1, which is 0. So I do get a critical value at x equals 0 this time. Let's test it. Our second derivative is 0 here. And I'm going to go ahead and put that second derivative in my calculator. It was e to the x minus e to the minus x. And I'm going to pick a number less than 0, maybe negative 1 for my first test value, and I get a negative second derivative. Let's try positive 1, and it looks like I get a positive second derivative. So the graph does change concavity from concave down to concave up, meaning that I do get an inflection point at x equals 0. Right? By the way, notice when x is 0, I'd have e to the 0 minus e to the 0, 1 minus 1, so that's actually going to be the origin, 0, 0. And as long as I'm right here, let's list the intervals. Concave down from negative infinity to 0, and concave up from 0 to infinity. All right, well, that didn't give me a ton of information, so I may have a little bit of trouble sketching this graph, but we might be surprised at how much we can tell about its shape, even with this small amount of information that we've been able to generate. The only point I know anything about is 0, 0, so that's the only point I'm actually going to plot. And I'd like to draw a graph that's always increasing, so it's going to have to go this way through 0, 0. It's concave down on the left side and concave up on the right side. So concave down coming into 0, 0, concave up going out. Notice because there were no critical values for the first derivative, I didn't try to make a horizontal tangent line this time at 0, 0. There is no place where that derivative is 0, so I shouldn't have one. So that's about the best I can do with the information that I've been given. Let's check and see how close we came. E to the x minus e to the minus x, I put that in as the second derivative, but did you notice that the second derivative was actually the same as the original function? It is. So I can just go ahead and graph this. What have I got from my window? That should be fine. And a surprisingly good graph, considering how little information we really had to work with. All right, let's pause there, and we'll come back and we'll do a couple more examples of graphs in the next video.